The next topic is voltage divider bias. The last biasing circuit what we have seen, it is a very efficient bias, right? So this is the voltage divider bias circuit you see. It's a common emitter amplifier. You have the load resistance RC, you have the biasing resistors R1, R2 here, and you have the emitter resistance parallel to a capacitance CE. The CE is called as bypass capacitor. And you have input coupling capacitor, you have output coupling capacitor. So other things are as usual. You have RE parallel to CE. So this is the common emitter amplifier, and the biasing is obtained by the potential divider R1, R2, which is operating across VCC. So it is called as voltage divider bias. So now we are going to substitute the H parameter model. So whenever I told you, whenever you have the circuit having AC components, you should short circuit the capacitances and you should short circuit the voltage. So if you short circuit the capacitance, you have here RE parallel to 0, because this capacitor is also short circuited, right? So anything parallel to short circuit will be 0. So this resistance will not come in the equivalent circuit, and these two capacitance also will not come in the equivalent circuit. So directly first from the given circuit we will be drawing the AC equivalent. From the AC equivalent we will be drawing the H parameter model. So RE is omitted in the equivalent circuit because when you short circuit this capacitance CE, the effect of RE is neglected. So this is the equivalent circuit. R1 and R2 will come parallelly and HIE will come. And this RE, if RE we usually will come here, right? So RE will come here. So, but here because you are short circuiting the capacitance CE, this RE will not come here. The effect of RE is omitted. So HFEIB RC, and output voltage I measure it across RC. This becomes a very, very simplified circuit. Okay, and I am considering this parallel combination of R1 and R2 as RB. So this parallel combination of R1 and R2 is given a name RB. RB equal to R1 parallel to R2. See here, I am giving it as R1 R2 by R1 plus R2. The formula is R1 R2 by R1 plus R2. And with that, you can see at the input side, all the three resistance are in parallel. And I have renamed this one as RB. So the input resistance will be equal to RB parallel to HIE. You can see everything is in parallel. There is no confusion at all. So Zi will be equal to R1 parallel to R2 parallel to HIE, and R1 parallel to R2 I know it is RB. So I can write Zi equal to RB parallel to HIE. It's a very, very simple like input impedance we get. And output impedance, if you see, it is RC parallel to infinity. So anything parallel to infinity is that resistance. So output resistance is also equal to RC. It is very simple here. Okay, it is very, very simple here. The input impedance, you see at the input side, all the three resistance are parallel. So it is R1 parallel to R2 parallel to HIE, and R1 parallel to R2 I have named it as RB. So it is RB parallel to HIE. Output side, if you see, the collector, you have two resistance. One is RC. Parallel to RC, you have current source. I told you the impedance of current source is infinity. So anything parallel to infinity is RC. So is that not equal to RC? And now voltage gain V naught equal to output voltage by input voltage V naught by Vi. Output voltage I measure across RC, and same way direction is differing. You see it is plus minus here, and how plus minus you are getting, the current is flowing from top to bottom to top, so the polarity is reversed. So it is minus I naught into RC, and I naught, you know, it is HFE into IB. So V naught equal to minus HFE IB into RC. And Vi, you know, Vi is what is available at the input of your transistor. Vi equal to IB into HIE. It is very simple. See, V naught, measure it across RC, use Ohm's law. V naught equal to minus I naught into RC. I naught equal to HFE into IB. So V naught equal to minus HFE IB into RC. And Vi equal to, at the input of transistor, you see Vi equal to IB into HIE. And divide both, A is equal to V naught by Vi. So minus HFE IB into RC by IB into HIE. So IB will get cancelled. So it is minus HFE into RC by HIE. So this is the voltage gain of your transistor. AV is equal to minus HFE into RC by HIE. Current gain, same way, minus I naught by IA. I told you current should flow outside the circuit, but since current is flowing inwards, this minus sign, minus I naught by II. And I naught, you know, it is HFE into IB. Okay, I naught is HFE into IB. So I can write that here. And in the input side, you see the total incoming current is II. And but I want only IB. So I am using current division. So to IB equal to total current into this is the opposite resistance. R1 parallel to R2 is the opposite resistance. So I'm writing it as RB divided by opposite resistance plus that resistance. That resistance is HIE. So IB equal to total current into opposite resistance divided by opposite plus that. So IB equal to II into RB by RB plus HIE. So substitute that here. So I naught equal to minus HFE into II into RB by RB plus HIE. So minus I naught by II is going to be AI. So AI is given by minus HFE into RB by RB plus HIE. So this is the expression for current gain we get. So AI equal to minus HFE into RB by RB plus HIE. So this is the four formulas we have for the voltage divider bias. One is current, one is input impedance, output impedance, voltage gain, and current gain. You see that voltage gain and current gain values are negative, which is indicating that for a common emitter amplifier, you will have 180 degree of phase shift happening between the input and output.